Welcome. Here we'll just recap the central limit theorem that we just talked about. So essentially what we're doing is studying a population, and we may or may not know the shape of the distribution of that population. So in my previous example, we knew the population was normally distributed, and we took a sample from that population and saw that the distribution of the sample means, so it's called the sampling distribution of the mean, was a bell-shaped curve. So I'm just going to highlight here. So X would be a value from a population, but instead if we took samples repeatedly and graphed all of those sample means, so that is my X bar axis now, that distribution of sample means would be normal, with certain conditions having to be met. So the deal here is that if we were to take a normal distribution and draw samples, the sampling distribution would also be normal, bell-shaped. But if our distribution is not normal, maybe it's skewed, or maybe we don't know what the shape of that distribution is, then our sample sizes would need to be reasonably large in order for this distribution to be normal. And just kind of a number we use as a guideline, sample sizes greater than or equal to 30, we would just say are reasonably large. So if this distribution was not normal, we would have to take samples of size not 10 or 15 or 20. We'd have to take sample sizes of 30 or more in order to have our distribution follow a normal curve. All right, there's some additional requirements here. We don't focus on something called the correction factor in this course. So if you do see a comment on that in homework, you can just ignore that. But generally speaking, there are always conditions that need to be met in order for theorems to apply. All right, and then finally, the big change here as we work with problems, X versus X bar, individuals versus sample means, is that the standard deviation of this sampling distribution will not be sigma as it was for the original population. So when we deal with sample means, the standard deviation changes to sigma over the square root of n. And this is called the standard error of the mean. All right, so I know there's a lot of theory there. Let's just jump in and do another problem. And I think in application, it always makes more sense. Okay, so number one, suppose that the average time it takes a person to assemble a toy is 30 minutes with a standard deviation of 6 minutes. So we have an average or a mean of 30 minutes. So the average person takes 30 minutes and a standard deviation of 6 minutes, and assembly times are normally distributed. So up here, this distribution now is known to be normal. X is the time it takes a person to assemble the toy. All right, so let's write down our population parameters. Always good to focus on correct symbols here. So mu, population mean is 30. And sigma, population standard deviation, is 6. And then it says, find the probability that a randomly selected person, so they're picking a singular person, we want to know the probability it takes them more than 34 minutes to assemble the toy. So this question is probability that. So if we're just taking a single person, so I often just say singular, just one, the variable that represents the time to complete the assembly of the toy is X. So X is the time for a person to assemble the toy. We'd like to know the probability that that's more than 34 minutes. All right, and we know to find probability, it's normal CDF. And I am going to just come down to the picture here for a second, just to remind you that when we use normal CDF, we have to get the order correct as we enter information on the calculator. We're looking for values of X greater than 34. So there's my 34. So greater would be to the right of it, in theory, to the right forever. So on our calculator, we'll be entering the lower bound first, 34, and then our upper bound will be our infinity substitute. Okay, so this graph, my blue one here, is the original normal curve, so that variable is x. All right, so let's get this in. So 34 is the lower bound, and then we do our substitute E99 for infinity. And then we needed our mean, which was 30 there, and our standard deviation of 6. All right, so back to the calculator. We're doing our distributions. Normal CDF, 34, comma, E99, comma, 30, comma, 6. And I usually don't close my parentheses, a little lazy, but I don't. We're going to be good. I'll round to 4 places, 0.2525, 0.2525. So there's a 25.25% chance a person takes longer than 34 minutes to assemble the toy. So on my graph, that's that vertical blue shading. So that's, I'd say, a pretty high probability. So that is the blue. And then we're going to see how that compares to what happens with the central limit theorem. So the central limit theorem applies when you're not picking a single person, but rather a sample. So suppose 9 people are randomly selected and asked to assemble the toy. Now we're going to find the probability that the mean for those people sampled is more than 34 minutes. Okay, so our sample size N is 9. So the central limit theorem tells us that the mean of the sampling distribution, so we're going to be looking for a probability concerning X bar, not X. And the mean of that distribution is the same as the original mean. So if you look on our graph here, the mean of either the red or the blue graph is the same. So the mean doesn't change. So that's 30. So just as a note here, if we don't write a subscript, it's assumed it's an X, but we could put it there for emphasis. So the mean of the sampling distribution is the same as the mean of the original population, and that was 30. The thing that we have to change is our standard deviation when we look at the sampling distribution, and that's sigma divided by the square root of n. So in this case, sigma was 6. So that's just that 6 from the start, and then we're dividing that by the square root of n, which is 9. So I'm going to make a note down here then that my red graph there is my X bar graph, my distribution of sample means. And 6 over the square root of 9 is 2, because the square root of 9 there is 3. So while it's true that this is 6 divided by 3 or 2, if we have an n that's not a perfect square, it's going to be important never to round values that we enter into normal CDF. So just for practice, even though the answer there is 2, I'm going to enter it on the calculator like that. All right, so let's see what this question looks like in symbols. We want to know the probability that. So because we have a sample, we're looking at the probability that the mean of the sample, so that's your X bar, and we want to know the probability that that is greater than 34. So the central limit theorem tells us when we look at that graph, it'll have the same center, but it won't be as spread from that center. So the standard deviation is smaller. It was 6 on my blue graph, there's less spread. Standard deviation 2 on that graph. So if more of the graph is towards the center, central limit theorem, more of the graph is centered at the middle, that means my area past 34, you can see my red there is getting much smaller. So that graph of X bar, let's find the probability that a sample mean is higher than 34. All right, so it's still normal CDF. And we're still going from 34 to infinity. The mean of that graph is 30. But the standard deviation is 2. And again, just for practice, I'm going to type it as 6 divided by square root of 9. Okay. So I'm just going to clear my graph there, calculator, and start fresh. So I'm going to distributions, normal CDF, 34, comma E99, comma 30, and then 6 divided by square root of 9. All right, and that's coming out to be 0.0228. Yes, 0.228. So that is smaller, a smaller area than the last answer. I'll write that as a percent as well. So there's only a 2.28% chance that it'll take 9 people on average more than 34 minutes. Whereas there was a much bigger chance it would take an individual by themselves more than 34 minutes to complete the assembly of the toy.